Hello, everybody. Today we are starting Unit 4. If you want to title your Unit 4, it's all about circuits. I'm pretty excited. This is a pretty fun unit. We're going to start our discussion of circuits with defining what a capacitor is. So let's get started. A capacitor is any sort of device that stores electric charge. And this is created by placing two conductors near each other. And exactly how that makes a capacitor we'll talk about here shortly. So one of the most common types of capacitors that we will discuss in this class is one called a parallel plate capacitor. So with a parallel plate capacitor, it's just what it sounds like. You have two conductive plates that are placed near each other, separated by some distance d. And each of these plates has some area A. That's the one that we'll deal with the most, and we have some formulas to describe parallel plate capacitors. Some that are a little bit more common in actual circuits are called cylindrical or rolled. And those, again, kind of what they sound like. It's a cylindrical device. So I have some of these in the classroom I'll show you when I'm back, but pretty much just like a little spiral, little like Swiss roll. So it's two parallel plates, but they're rolled up so that you can have a greater area in an overall smaller package. And we're going to start talking about circuit diagrams, and we want to be able to put capacitors in our circuit. So circuit diagrams here. How we draw a capacitor in a circuit. So let's say this is a wire. You just have two parallel lines to represent a capacitor. A symbol that we'll start seeing today is for a battery. A battery looks a little bit different, kind of similar. It's got two lines, just one is shorter, and imagine they're both straight there. And this is a battery, so it's slightly different. Has one long and one short side. The long side is the positive side of the battery, and the short side is the negative. Okay, so let's talk about how we charge a capacitor. How does it collect charge? So this happens when we connect it to a battery, which we'll talk more about tomorrow, but a battery is a source of delta V. Remember, that's electric potential. So if we connect a capacitor to a battery, the capacitor will become charged. So let's draw this little circuit diagram. So let's say I've got a battery here. So I've got a positive and negative side of my battery. And these lines, which should be straight, it's just hard to draw, should be connected to a capacitor and then back to the battery. So this is a wire and this is a capacitor here. So what happens when we connect this capacitor to the battery is that the negative side of the battery will cause this side of the capacitor to become negatively charged. They're all in contact here, so those negative charges build up on this right side of the circuit, where the left side becomes positively charged. So we say that this capacitor now has some positive amount of charge on one side and some negative amount of charge on the other. The battery is a source of electric potential, so delta V. So you might see something like a 3-volt battery or a 9-volt battery. That's what this is talking about. And when this is connected in this simple circuit, we'll end up with the same electric potential difference across the capacitor that we have across the battery. Okay. So if you want to make a note of that, same delta V across the battery and the capacitor. and each plate collects the same amount of charge. And we call that charge Q. So our first formula is going to be relating this electric potential and amount of charge that is collected. And the formula is right here. Q equals CV. So Q, again, is charge, the amount of charge that's collected. And that's in coulombs. V is electric potential. And that's measured in volts. And C is a new measure, and it's called capacitance. Obviously, we use the capital letter C, and the unit is a farad. So a farad, 1 farad is a huge amount. We're usually going to be dealing with, kind of like we did with last unit, but things that are to the -6 power or -9 power. The capacitance of a capacitor depends on the geometry of the capacitor itself. For a parallel plate capacitor, the capacitance equals epsilon naught times A over D. That epsilon naught is just a constant. This is called, let me remind myself over here, vacuum permittivity. I think I added an extra T there that you didn't need. But it's a measure of, again, a nature of a vacuum and how electric fields propagate. That part's not as important, but it's just a constant that we're going to use to calculate capacitance. And again, when we have a capacitor, this is for parallel plates. 2 parallel plates connected. We've got distance between them D and area of the plate A. So by collecting charge, we're also collecting energy in a capacitor. These are the 2 different formulas that you have on the formula sheet to calculate the energy stored in a capacitor. The subscript is C to designate capacity. This is energy stored in a capacitor, but this is still electric energy. And we measure that in joules. Right. Last topic for today is a dielectric. So a dielectric is essentially an insulator between plates. So most capacitors have some sort of material between these 2 plates, because I want to be able to get these plates really, really close. So in order to get them really, really close, sometimes a different insulating substance is added between the 2 so we can minimize that distance D without the plates actually touching. So by decreasing D, you can increase capacitance and store more charge. So we're going to take that formula that you saw earlier and add this little thing out front. It's a Greek letter kappa, but it's the dielectric constant. So what that does, it depends on the material, and you'll substitute different values in depending on the type of material that exists between the plates. Most often, you will see a capacitor where we're just assuming there's air in between the 2 plates, so we can say that's the number 1 and not have to deal with it. But if you're told that there is a dielectric material between the plates, you'll probably most often be given what that number is or asked to find it if you're given the other values. So let's do an example. So we have a parallel plate capacitor, and we're given the area here is 5 times 10 to the -5 square meters, with a distance between the plates of 10 to the -4 meters. And the dielectric material that is between the two plates is paper with a dielectric constant of 3.7. Oh yeah, also the dielectric constant is unitless. There's no unit to go along with that. And we're also given that this is connected to a 10-volt battery. So we want to figure out, first question, how much charge can the capacitor store? So we're looking for Q, and our new formula is that charge equals capacitance times potential. I don't know what capacitance is yet, so let's use that formula to calculate capacitance, which is kappa times vacuum permittivity times area over distance between the plates. So that's 3.7 times 8.85 times 10 to the negative 12th. Area that we're given all over 10 to the negative 4th. And we get capacitance is 1.6 times 10 to the negative 11 farads. So farads are the unit for capacitance. Take that and plug it in to our first formula. Multiply that by 10 because that is the voltage of the battery. And you get Q is 1.6 times 10 to the negative 10 coulombs. That's the amount of charge that this can hold. Okay. That's kind of ugly. All right, and the last question, how much electric potential energy is stored in the charged capacitor? So that's looking for UC. And I would just pick whichever equation is easier, either 1/2 QV or 1/2 CV squared. Could use either. So let's just say we use 1/2 QV. So 1/2 Q is 1.6 times 10 to the negative 10, and V is 10. And we get something like 8 times 10 to the negative 10 joules. That's all for today. Thanks for listening.